Okay, so in the previous video, I claimed that a electric charge moving produces a magnetic field. And I kind of told you, suck it up, deal with it for now. We'll talk more about it later. Okay, it will continue to come up throughout the course, but for now, I'm going to at least give you a little bit of a peek behind the curtain there. And let's actually, at the very least, let me prove to you that that's true, that a moving charge produces a magnetic field. Okay, so I'm actually going to just try and recreate really quickly Orsted's experiment here so you can see what I mean. So Orsted was actually, the cool thing is he discovered this completely by accident. It was this revolutionary discovery that kind of changed the way we look at physics forever, okay? Well, especially the electricity and magnetism branch of physics. We'll get to that in a sec. But um, what he was doing was actually just trying to show students that when you run a current through a wire, it can produce heat. He was a professor at a university, right? And he was teaching a class, and he was just showing them if you run a current through a wire, so allowing charges to flow through the wire, he was just showing them that the wire will get hot, right? Okay, and so when he was doing that, he had a compass on his desk nearby, and you might have just caught what happened if you had a keen. Okay, and okay, and so when okay, and so when he was okay, and so when he was doing suddenly a current through the wire, what happened to the compass needle? It actually got deflected, right? You can see that here as I'm connecting and removing the circuit, right? The compass wire is actually becoming deflected. So as a compass is a magnet, right? It seems that electricity is causing some kind of change in a magnet. Now, only a magnetic field should do that, or at least up until the time of Oersted doing this, that's what we thought. Magnetism and electricity were two separate phenomena. Okay, so maybe that doesn't sound like a huge deal to you at the moment that moving charges can produce a magnetic field. Again, remember, electricity is the flow of electrons, so that is moving charges, of course, right? But think back to the basics of our domain theory, right? How did we get even the very first step towards becoming a permanent magnet, to becoming ferromagnetic, right? You needed those electrons to be whizzing around, and then you needed to be whizzing around in a way where they didn't cancel each other's magnetic fields out, right? This actually now explains domain theory, okay, is now explained by the electrons moving within a substance, okay? So the idea that a moving charge created a magnetic field was actually very important for beginning to even wrap our heads a little bit around the phenomena of magnetism. And this was huge when Oersted discovered this. Okay, this was huge. Up until this point, electricity and magnetism had been considered completely separate phenomena, right? Like you might have even, right? I'm not sure that I knew that before I took Physics 30, that electricity and magnetism were so intrinsically related. This kind of proved that they are two sides of the same coin. Okay, why else does it matter? Well, there were these electromagnets. So we have your permanent magnets, right? Those are kind of the ones we've been looking at, the ones I've been sprinkling iron filings on. We've been looking at the field of it. But there's another kind of magnet we've sort of neglected up until this point. That's something called an electromagnet, okay? And that is, as it suggests, right? It is a wire with current. So a wire with current, in other words, the flow of electricity, right? The flow of charge wrapped around a metal bar. Okay, I'll show you one of those in a second here. But the point is, this movement of charge, right, was essential in explaining magnetism. You don't have magnetism or magnetic fields without the motion of charge, as Oersted sort of proved accidentally. Okay, so now that we can kind of accept, or at least I've showed you, maybe you don't accept it, but you're going to have to because I just showed you that a moving charge produces a magnetic field. Let's see if we can start to break that magnetic field down a bit, quantify it, right? And analyze its direction with a little more rigor than walking around with a compass, okay? So how much current produces exactly how strong a magnetic field? We're not going to necessarily answer that right now, but we can at least quantify current itself, okay? So current is the rate at which charge passes through a point in space. So the rate at which some amount of charge passes through a point in space. Whenever we're talking about a rate, we're essentially saying how much of it happens per unit time, right? Usually per second. So for current, we're saying how much charge passes per second at a point, right? So where have you heard current before? Well, you've heard of it in the context of water, probably, right? So if you imagine a river with a strong current, what does that mean? It means the water is flowing very quickly, right? Or a lot of water is passing through. If you just kind of stand there and you're going to count the water molecules, you have some detector there that's going to count every water molecule. A high current, right, would have tons, lots and lots and lots of water particles pass your detector every second, right? Whereas a lower current, right, a more slow moving river, or not necessarily just slower moving, but maybe a smaller river, right? It could be the same size and flow slower. It could be a smaller river, so there's less water flowing, okay? But either way, whether it's big and just moves slowly or smaller and moves at the same rate, okay, either way, you're going to detect fewer water particles per second passing your whatever imaginary detector you have that is able to detect the water particles, the number bajillions and bajillions of water particles, okay? So what does that look like? It's a very similar analogy when we go to electrical current. It's actually the same thing, except instead of water, now it's charge flowing through some point on your quote unquote river, which would usually be a conductor, although it doesn't have to be. What all it is a point in space, okay? So how does that look as an equation? We have I, the current, is equal to the amount of charge divided by the amount of time, right? So charge per unit time, okay? So if we have a lot of charge passing through, right? If that's a big number, then we have a lot of current. Or if we have, in a very small amount of time, we still measure a decently large charge passing through, that's a lot of current, right? So whenever there's a lot of charge per unit time, you have a high current. So think for a sec, what would be the units that we would use to describe current? Okay, you might be thinking, well, I know charge has units of coulomb. I know time has units of seconds, so you'd be saying a coulomb per second. Okay, and you're absolutely right, except we give that a name. We call it an ampere. Okay, the symbol is A. Sometimes you'll see amp, but for the most part, you'll just see A. And just like we said, 1 amp is the same as 1 coulomb per second. Saying that there are 3 amps of current in a wire is the same as saying that, hey, every second, 3 coulombs worth of charge pass through this point in the wire. I keep saying wire. It could be really any point in space, okay? That's how we define current. Usually, yes, it's a wire, but we will see free charges as well later. And the idea of current doesn't necessarily go away, although it is less applicable there when we go to analyze. Okay, so there we are starting to quantify current. What about the direction, though, of the magnetic field that's going to be produced? So we haven't quite quantified the magnetic field. We're going to get to that later, okay? But we've at least quantified current. But remember, we started this out saying, how do we think about the magnetic field produced by a moving charge? Okay, because all we know right now is that it does do that. This is where things start to get a little bit different than past phenomena we've dealt with, okay? So the magnetic field produced by a current is perpendicular to the current that caused it, okay? So at a 90-degree angle, right? It will be at a 90-degree angle. So we're going to take a look at how that will look in a sec, okay? But first, something really, really important, okay, is a little bit of a mistake that was made in our past that has kind of stuck with us, okay? A lot of people blame Benjamin Franklin for this, although he kind of had to make a guess. He did. He turned out to be wrong. But when we were first kind of studying all this current stuff, right, we knew there was charges involved, and we knew there were opposite charges. We kind of had to give them an opposite name. And we said, which ones are flowing when we talk about current? And as we know, it's really electrons that move, okay? But when Benjamin Franklin was deciding what's moving, he took a guess basically and said, I think it's the positives that are moving. And we said, okay, great. So we'll just say the positives are the ones that flow during current. We took that, we went and studied a whole bunch of physics with that assumption, wrote a whole bunch of textbooks, kind of figured it out, right? Understood all these aspects of electromagnetism, and then we kind of figured out, oh, whoops, it's actually the negative ones that move. So it was either go back and rewrite all those physics textbooks, change all of our kind of understanding, or just say, hey, we'll define current as the direction a positive charge would move, okay? Even though it's really the electrons that flow. It doesn't end up being really a big deal, other than that you have to know when they say current, okay, or conventional current, they're talking about how a positive charge would move, right? And sometimes positive charges will move for us. We will see that, okay? But in a wire, it is the electrons that move, as we know, okay? All right, so I'm going to show you a video. It is very old, but it's actually very good. I looked around, I couldn't find one. It has a lot of really good visualizations of these concepts, okay? So we'll watch that, we'll come back.
When you're out on the water, it's great to be fishing. But fog does tend to dim your enthusiasm. Don't despair. Your handy compass works in rain, hail, and yes, even fog. Unless, of course, there is something which throws the compass off. In which case, you might be in for a bit of a surprise. A compass needle is simply a magnet, and an attractive force exists between magnets and iron objects, even at a distance and even through the vacuum of space. It's as if invisible hands pull the magnet and metal together. In this way, magnetism is similar to the forces that charged particles exert on each other. These forces act over a distance in the same mysterious way. During the 17th and 18th centuries, electricity and magnetism developed as separate sciences and were believed to be unrelated. Then, in 1800, Alessandro Volta developed a device that paved the way for a change in this view. His device consisted of copper and silver coins, arranged in a column and separated by pieces of cardboard soaked in salt water. When he attached a conductor to the top and bottom, like this, and brought the two ends together, a spark resulted, indicating that a flow of charge was occurring. Volta's work eventually led to the development of batteries, which could be used as sources of continuous charge flow. A battery like this was used by Danish physicist Hans Christian Ørsted in 1819 to conduct an experiment in which he hoped to prove conclusively that electricity and magnetism were not related. At first, the demonstration seemed to work. When the switch was closed, the compass needle, which was perpendicular to the conductor, didn't move at all. However, when Professor Ørsted repeated the experiment, this time with the needle parallel to the conductor, and the switch was closed, the compass needle reacted instantly. So it seemed obvious that electricity and magnetism were somehow related. As a result of Ørsted's experiments, French physicist André Ampère made a detailed study of the magnetic field about a conductor carrying a charge flow. Using iron filings, he demonstrated that there was a magnetic field around the conductor. The pattern formed by the iron filings created a series of concentric circles. Depending on which way the negatively charged electrons flow through the conductor, the magnetic field around the conductor will be in one of two directions. With the electrons flowing this way, the magnetic field around the conductor is in this direction. Reversing the flow of electrons doesn't affect the shape of the pattern, but it does affect the direction of the field. Reverse the electron flow through the conductor, and the magnetic field direction will reverse as well. Our left hand gives us a convenient method for correctly predicting the relationship between the direction of the magnetic field around the conductor and the direction of electron flow through the conductor. This is the left-hand rule for conductors, and it states that if the left hand is placed around the conductor, with the thumb pointing in the direction of electron flow, the fingers will curl in the same direction as the magnetic field. Reversing the current means that the thumb must now point in the opposite direction. Although the fingers now curl the other way, they nevertheless indicate the new direction of the magnetic field. Of course, if the flow of charge is interrupted, the magnetic field collapses immediately.
All right. So now we are getting into these idea of these vectors that are related to each other through perpendicularity, right? So it's no longer, okay, it'll be in the same direction or in the opposite direction. We're actually looking at things that are going to happen at 90 degrees to one another. And so it can get a little bit weirder to think about which way things will go. And you kind of need a tool to help you along with that. Luckily, we have attached to us two things that can very much help us visualize things that are at 90-degree angles to each other, not only in 2 dimensions, but actually in 3 dimensions, okay? And those are our hands, okay? So this part of physics is actually really fun. It kind of gets physical. You get to kind of move around a bit. I like this stuff. So what are hand rules? They just help you understand how the direction of the current or electron flow, okay, relates to the direction of the magnetic field it creates. We'll eventually see there's actually a third thing it can tell us about as well, but we'll get there. So very important to not mix these up. If you mix these up, you'll be approaching the problem from the wrong angle. You'll be approaching the problem from the wrong angle from the very beginning, from the very get-go, okay? So this is crucial. Always use your left hand for electron flow, okay? And it might not always be an electron, but anything negative, okay? Anything negative you need to use your left hand for. This applies to every hand rule we're going to use. Now for the anything positive, you're going to use your right hand. So right hand for current, or again, the direction a positive charge moves. All right. So my trick for remembering this, sorry to all you left-handed people, but for most of us, we're right-handed, okay? So if you're right-handed, I think of it as, hey, if I get to use my right hand for something, that's a positive. That's a good thing for me, right? That's a good thing. It's a positive to be able to, for example, write with my right hand. If I had to use my left hand, that would be a bad thing. That would be negative. My writing would not look good. So I think right hand positive, that's a good thing. Left hand negative, that's a bad thing. So if you're left-handed, sorry, you're gonna have to flip those or come up with your own way of remembering. But always left hand for negatives, right hand for positives. A quick note before we move into actually putting this into practice is that we're very good at drawing vectors in 2 dimensions, right? We're very good at showing something going that way or going that way, right? But now that we're going to move into perpendicular things, there are going to be times where things are not moving within the plane of the page. They might be coming at us or going away from us, okay? So how do we visualize that? Well, let's imagine again, okay, you had a vector like this, and I'm just going to say, here's your eyeball. So you're looking at the vector, and it's actually coming right out of the plane at you. How do we show that? We would use a dot, okay? So now this is, you are looking at this, right? That vector is coming at you, okay? And the trick to remember that is picture an arrow, right? If you picture literally an arrow, like not a directional arrow, like a bow and arrow, right? If you picture a bow and arrow, okay, over here you have a, if it's coming at you, you kind of see just the point. You just see the dot of the arrow, right? You just see the dot of the arrowhead coming at you, okay? Now what if it's going away from you? So what if you're looking at a vector that looks like this? So here's your eye, okay? What does that look like? How do we represent that in 3 dimensions? So if a vector is going away from you, we use an X, okay? So this is going into the paper right now. This is coming out of the paper towards you. So how do we picture that? Well, imagine looking at this arrow from behind now, okay? You would see the kind of tail feathers of it, right? It would look like an X from behind. So arrows are going away from you, they look like an X. Arrows are coming towards you, they look like a dot. So a vector out of the page, dot, vector into the page, X. All right, now to actually put this in practice, I'm gonna have to come on camera a bit and show you my hands. But before I do that, let's just really quickly go through the hand rule itself, and then I'll show you some of it in action. Okay, so the first hand rule, okay, sometimes called the wire grasp rule. Why? Because you're going to be acting like you're grasping the wire, okay? Now this is for straight currents, okay? So this is for when currents are moving in a straight line, essentially, okay? So your thumb points in the direction of the current, okay, or electron flow. Pop quiz. If it's current, which hand are you going to use? Your right hand. If it's electron flow, which one? Your left hand, okay? So positives get the right hand rule. The right hand rule. This goes for all of our hand rules. Negatives go for the left hand rule. Okay, then what's the point of this? Well, your fingers are going to show you the direction of the magnetic field. Okay, so your fingers will actually show you not only where the field lines kind of are, where you should imagine them to be around the wire, but also what direction they go in. So the fingers will become the direction of the magnetic field. Okay, so thumb is the direction of motion of charge, whether it's positive or negative, and the fingers are the direction of the magnetic field. Let's see this in action now. Okay, so first things first, do not take my word for it, right? Don't just learn a trick and accept it. Let's actually investigate it, see its validity, right? How good of a trick is this? So before we do that, I'm going to have to kind of explain this setup to you because I know it looks a little bit, what am I looking at here? Okay, so, whoops. This here, you can see, is coming towards you is a wire, okay? I tried to get it about as vertical as possible. This is essentially a wire that is running vertical. That's the portion of the wire we're going to be interested in. So this is a straight conductor, right? The current will be flowing straight through here, okay? So I have an end here and an end here. If I hook them up to a power source, such as a battery, right? If I hook them up to a battery, I will have electricity flowing as it makes its way from one terminal of the battery to the others. Okay, there you can kind of see it. So there's a positive. This terminal is the positive terminal. This terminal is the negative terminal, okay? So I'm just going to label that here on the whiteboard. So I have here, if we're looking at our battery like that, we have our, the way it's sitting, this would be our positive terminal, and this would be our negative terminal, just so you can kind of keep it straight as I hook up the wires. So what does that mean in terms of a battery? Okay, well, the positive terminal is essentially where electrons would like to go, right? They would like to flow, they would like to get away from the negative terminal and flow towards the positive terminal. So if I hook up this one here, which connects, you can see to the top, if I connect this end of the wire to the negative terminal, electrons are now trying to come this way, right? Except the circuit is not complete, so they can't actually do that. But if I now complete the circuit, okay, what is happening? Electrons are now coming, they're coming around. This is just to get it up here, but now they are flowing from here. Okay, we'll trace it. They go up to the top, and then in the straight portion, they are going down. So how are they moving relative to us? They are moving away from us. So electrons are moving away from us. Which direction would current be? Well, that's right. It would be towards us, right? Because how would a positive charge flow, which is what current direction is? It would flow the other way of an electron, right? It would go from the negative terminal down and then up towards us and then back around on this part of the wire that we're not really considering, back to the negative terminal. That's what a positive charge would do. Okay, just going to unhook these because they do get quite hot, okay, until we're ready. So we need to now figure out what is the magnetic field direction around this charge. But first, okay, let's just use our new kind of skills here to label the direction of, let's do electron flow first. Okay, let's do electron flow. So as we said, if I hook them up the way I had them there, right, then the electrons would come up here and then down. So in the section of the wire we're interested in, electrons, this is going to be electron flow, not current, okay, although we could do either one and it would work the same way. Electron flow would be down this way, away from you, or into the page. So picture an arrow. If an arrow is going away from you, it's going to look like that, right? That's the tails of the arrow as it heads away from you. So as it heads through this wire, it goes away from us, okay? And as we now know, magnetic field will be induced by that moving electron because it is a moving charge. So I'm going to hook it up and let's try to test it out. Let's see what happens when we look at the magnetic field around the current carrying conductor, the straight current carrying conductor. Remember, how can we determine magnetic field direction? Well, we need a test magnet, right? The hand rules work, but because we've already kind of established the directions of magnetic fields with test magnets, and then we apply that to current carrying conductors. So we'll use my test magnet here, my compass. Remember, the north pole of the compass points in the direction of the field. So we can use this to kind of map out the direction of the field around this current carrying conductor. In this case, we're interested in electron flow, which is into the page. So I'm going to hook it up and we'll take a look. So there we go. We now have electrons coming and flowing down the page because I've connected the terminals of the battery. Let's take a look. So as I go around the wire that's here, right, you can kind of see, okay, the electrons, or sorry, the magnetic field seems to be moving, what's that, counterclockwise, right? The electric field seems to be following. So if I were to draw it, for example, here, right, here, it's kind of up, right? If I were to draw it over here, the electric field's in the exact opposite direction, it's down. Okay, what if I draw it down here? It's to the right. Okay, and up here, it's to the left. So as I go all the way around, and I'm just gonna unhook these because they are getting hot, I can actually smell them. Okay, so as I go all the way around, right, you'll remember, can't do it now because there's no current flowing, no charge moving, you need the charge to be moving. But as I moved it around, the magnetic field, sorry, that was induced by the current, which essentially means created, was in a circle like that. Okay, let's try applying our hand rule to what we just saw, what we just actually observed, right? As I move the compass around, this is how the north needle pointed, which we know kind of determines field direction, or it doesn't determine it, but lets us visualize it. So if the electrons were flowing away from us, okay, first of all, if it's electron flow, which hand rule, left or right? Left, because the electrons are negative. So I need to take my hand, my left hand, and the claim is that if I point my thumb in the direction of the moving charge, right, then my fingers, if I curl them, if I pretend like I'm grabbing the wire, should show me the direction of the magnetic field. So you're gonna try this at home too, okay? So I'm gonna take my left hand, I'm gonna point my thumb in the direction that electrons move, and then my fingers should point in the direction of the magnetic field. And what do you know? I can go all the way around and it's always true, right? So if the electrons are flowing into the page, I go like that, and sure enough, it does work. It shows me the direction of the magnetic field. Okay, what if I had started this out differently? What if I had said, let's not think about electron flow, let's think instead about current. Let's think about current. Now remember, is current a real thing? Not in a conducting wire. There's not actually positive charges moving. But again, we will deal with positive charges that do move. They just won't be in a solid. So it's not the craziest thing in the world to think about positive charges moving. But again, for a current carrying conductor like this, it is kind of imaginary. It's the electrons that are flowing. So if it was current, how would the direction change? Well, it would do the opposite of what the electrons did, right? So instead of coming up and then going down in this wire away from you, they would have flowed the other way, up the wire. Positive charge would have moved up the wire towards you. So how do we represent that? How do we represent that visually on paper? Well, we can't really draw something coming out of the paper, but we can represent it with an arrowhead. See how that arrow is coming right at you? Okay, so now if the hand rules work, they need to work for both scenarios, right? They need to work for what a positive and a negative charge would do. As long as we imagine the motion of the charge correctly, then the magnetic field should still kind of end up in the same direction. So now we're dealing with current. Should that be my right hand rule or my left hand rule? Well, we have our current, our imaginary positive charge is moving through the wire. Okay, so I'm going to take my right hand, right for positive, left for negative, right hand. The thumb points in the direction of the charge, and then the fingers are supposed to show me the magnetic field direction. So let's take our right hand. If the current would be coming right at us in our example, so the current would be coming right at us, so I'll point my thumb at you, and then my fingers become the magnetic field direction. Aha! Look at that. Works perfectly, no matter where you are there. So if you're kind of panicking, saying, how do I know if I should use the current or electron flow? Doesn't matter as long as you think about it right? I would have got the same answer either way, whether I had started by thinking about current or started by thinking about electron flow. Left hand with electron flow, right hand with current. Either way, you get the same magnetic field direction. Cool. Okay, and just in case any of you are haters and say it's fake, looking at you, Jex, just kidding. I'm going to run it one more time, and then I'm going to use the iron filings to see if we can actually look at the magnetic field lines. Okay, so again, I got to hook it up to the battery. I'm going to do it off screen, but just take my word for it. Okay, I'm hooking it up the same orientation so that the electrons are going to flow up here to behind the camera where you can't see, and then continue down through the wire to complete the circuit. So electron flow is going this way, okay? The iron filings aren't going to tell us direction, but they will allow us to kind of see the field lines. Okay. Now, it's not quite as obvious as it was with our bar magnets because A, those were stronger magnetic fields, and B, the setup was just a bit easier. But if you take a look here, look, see those? See that kind of concentric circular pattern that's floating around there, right? That is the magnetic field, okay? And as we can see at all points, it's circular, perpendicular to the flow of the electrons. Okay, now quickly I want to come back to the idea of the perpendicular part. Okay, so here we have the one we drew before with our compass and mapping out the uh, field direction based on the direction of the current, right? When we did electron flow, it looked like this. Okay, same magnetic field. If you want to remind yourself, you can use the hand rules again to get there. Left hand rule here, right hand rule here. Okay, current, E minus flow. Okay, so what do I mean by this perpendicular part? Because we're used to seeing perpendicular stuff like this in two dimensions, right? We would say, okay, those are at a 90-degree angle, or these two vectors are clearly at a 90-degree angle. But in 3D, things can be perpendicular as well, right? So for example, right now, this marker is perpendicular to the table, right? Or if I hold the board like that, notice the marker is perpendicular to the whiteboard, right? That doesn't change because I hold it like this. It's still perpendicular to the whiteboard. So you can see it in flat, that makes sense, but it's still true that it's perpendicular. I could make another thing perpendicular to it. So now that arrow is perpendicular to the marker, right? Okay, so when we're looking at this, is the direction of charge motion perpendicular to the magnetic field, like we kind of had said? Well, yes, let's think about it. I'll use the markers to kind of clarify here, right? I have, for the current, that's a dot, so that means it's coming out of the page. So I'll use this, the arrowhead of the vector, I'll use this to be the tail, but if it's coming out of the page, it would look like that, correct? Okay, so that's coming at you. Now, what is the field direction? Well, it's always, no matter where it is, okay, notice it's perpendicular. Does it look perpendicular? Maybe not from your angle right now, but think about it, right? How are these two related? Okay, you okay with that direction-wise? Look at that, perpendicular. Okay, so this vector looks like this one looks like this. So kind of like the one we had drawn a second before, they are also perpendicular, right? Now, nothing changes over here. Now it's into the page, right? Now the X is into the page. The magnetic field hasn't changed, okay? So at any point, take it, and they are perpendicular, right? If they weren't perpendicular, these would not be flat in the paper. They might be coming a bit up, or they might be going a bit down. But for them to be perpendicular, this one's flat in the plane of the whiteboard, right? And so if it's in the plane of the whiteboard, and you agree that this is perpendicular to the whiteboard, well, then you agree that these are also perpendicular. These are all just the examples in the notes. I've just made them a bit bigger here so they'll show up on paper. So these are the exact ones that are on page 5. Okay, so let's just kind of see that's all kind of labeled for you, but that's no fun. Let's see if we can confirm how they've labeled it. Okay, so we have the wire grasp rule. So we have to first always figure out, are we looking at electron flow or current? And if they don't tell us, we should be able to figure it out and use whichever one. As long as we do it correctly, it actually won't end up mattering. So here we have, see why it's called the wire grasp rule? Here's my wire, okay, right? Think back to before when I had this vertical, it's not actually hooked up to anything now, but just for the sake of visualizing, right? When I had this like this, what was I doing to determine the direction? Well, if the current was out of the board at us, right, I could grasp the wire, and notice how now that matches up with what we said, right? Current, if it was out of the board in the wire up towards us, then grasp the wire and then think of it that way. What if you're doing electron flow? Well, switch hands, go to your left hand, right? And then put the charge motion, the electron motion, the thumb into the page and grasp the wire. Aha, lines up with magnetic field, right? Either way you do it. So that's why it's called the wire grasp rule. Okay, back to this one, electron flow. So left or right hand? I told you, but left hand, right? Electrons are negative. I think of it as a bad thing if I have to use my left hand because I'm right-handed. So grab the wire, right? Point your thumb in the point of the in the direction that that charge would flow in the case of electrons, right? In the case of the left-hand rule, the direction that electrons would flow. So point them along the wire and your fingers will show the direction of the magnetic field. So it might be kind of hard to see here, but yes, they've done this correctly, right? You might not, if you can see, okay, the magnetic field is drawn as being that way. Okay, cool. Look at the next one. All right, so for the first time now, you're seeing this B field. Let's go back to here. I just want to show you, okay, magnetic field. We've just been calling it magnetic field the whole time. It does have a symbol. It is B, and it's a vector, so it has an arrow. Okay, so this green thing I've been drawing, sometimes they even just call it a B field, but it is a magnetic field. That's the symbol, okay? So there we go, new symbol, magnetic field, B. So looking at this guy, okay, this is a common way of wording it. It says here, they curl counterclockwise from the point of view of an observer at the left. Okay, so that's a common way that they might be ask you to determine the field direction. So let's just imagine, okay, we are an observer over here. So we have, this is where our eye is. What do we see? Okay, well, we see, let's use our hand rule. Now notice, what's this symbol? I is for current. Now, is current electron flow? No, it's the direction that a positive charge would flow, right? So do we use our right hand rule or our left hand rule for current, for I? We're going to use our right hand rule. Okay, so like they've set up for us here, but they know how to do it. We're trying to see if we know how to do it, okay? So let's try ourselves. So our thumb points in the direction the charge would move. Since we're talking about current, we're imagining a positive charge moving, so we'll use our right hand, not our left hand, okay? So we'll take our right hand, we'll point our thumb in the direction that the charge would move, so it would start in the wire here and move along that way, okay? And then our fingers show the direction of the magnetic field. So question for you, if you're on that side of the wire, okay, if we're looking at the magnetic field on that side of the wire, that's on the other side down there, I can't go put my hand through the table, but you know what I mean, okay, which way's the field? Well, it would be, over there, it's, my fingers are pointing down, right? So it's down over there, okay, down over there, kind of behind the wire. But just like they've labeled for us here, it's hard to kind of think it, but there we go, right? If I flip back, well, now on this side, oh, that hurts the arm. If I go this way, right, I've got the field going up. See, up, just like they've labeled. Okay, so if you're over here, what do you see? Well, you kind of got to think about it, right? Kind of imagine tilting this whole thing that way so that you're actually looking at it. But if you're over here, then kind of on the right side, right, on the right side, closer to us right now, for an observer over there, that would be their right side. And then on the observer, their left side would be down like that. So what does that look like? Aha, right? Up here, it would look like that. Down there, it would look like that. So which way is it going? Whoops. Which way is it going? That is the opposite way a clock moves, so counterclockwise. Okay? Okay, another one. This is actually very similar to our setup that we just had, right? I took a compass and moved it around a vertical current carrying conductor. So let's see. First things first, what's that? I. Okay, that is current. So this is right hand rule, right? Current is where direction a positive charge would move. And they've showed us here, okay, they were nice enough to actually show us which way the current moves. They also could have just said positive terminal and negative terminal of the battery, okay? That would have been fair. And I just want to show you something that they also could have said. They could have not actually drawn out the battery. This is something you need to get used to seeing. They could have, instead of just drawing out the battery, they could have gone like this. Okay, this is kind of the symbol for a battery. The smaller terminal is always negative. The larger terminal is always positive. So just so you know that, okay, just in case you encounter it. So we have our negative terminal here. Okay, well, they've already told us current goes this way, but let's think about it in terms of the battery. Remember, electrons, what do they want to do if they're here? They want to get away and go to the positive, right? So electron flow would be this way. Our current is what a positive charge would do. So what would a positive charge do? If it was here, it would want to get away and go over there, right? Okay, so as we've established, yes, I agree, current will flow this way. So we'll use our right-hand rule here, okay? And imagine if I'm moving up in the wire, that along that wire, what is the magnetic field? Aha, well, if I'm here, yeah, I agree. It's going to be kind of this way, right? And as my right-hand rule says, as I get to here, the closest part to us, yep, look at my fingers, they're pointing that way, right? So good enough. That makes sense. Okay, keep wrapping around. Ooh, twist, and then sure enough, that way. And then what about in the back? Yeah, they're pointing that way. That makes sense. Now, I can hear you saying, okay, but geez, what if I don't notice that? What if I accidentally use the left-hand rule? Don't worry, as long as you think about it correctly, left-hand rule should give me the same result. So let's take our left hand and say, what would a negative charge do? Where would an electron actually flow? So like we said, it would start here, choop, choop, choop. Or we could just take the fact that since it's a negative charge, it would do the opposite of what the current would do. Okay, so it would do this, right? Do we get the same result for our magnetic field? Well, looking at that guy, yep, right? Use a different color so you can see when I switch to left hand just to see. Okay, so left hand will go that way. And sure enough, if I'm there, it's going to go that way. What about if I'm in the back? It's going to the left. What if I'm over here? Yep, it's kind of, can't get my hand at the right angle, but yep, it's coming out, kind of towards and downish, right? And then here, it's going over towards the right of the page. So you get the same B field, the same magnetic field, no matter which hand rule you use, as long as you think about the direction that that charge would move correctly. Okay, similar idea here, just shown a bit of a different way, so you can see the B field, right? It looks like that. When we look at the B field here, right, notice it's always kind of tangential to the circular path that it goes at any given point. This is a lot like our circular motion, right? The idea that the velocity was tangential at any point along its path. If the string were to break, it would go that way, right? So at any point, the B field, the magnetic field, is just kind of tangential to the circular path, just like we saw before. Oops, I shouldn't have made those red because I did that. Well, they did that with the right-hand rule. So last one here in your notes. This is going to make it a little more 3D. We can kind of deal with it here. So we have, okay, B, again, what's that mean? That's the magnetic field, okay? B arrows penetrate board here. Don't worry about it saying board. That's nothing technical. It's just that normally you'd be looking at this on my smartboard, right? So they're going, these are X's. So again, picture an arrow, right? If an arrow is showing X's, is it moving away from you or towards you? Moving away from you, right? So those are going down. Those B field lines are going down, okay, into the plane of the page. What about these guys? They're dots. Well, those are coming at you, right? So what does this magnetic field actually look like? Well, it's coming out of the page here, right? Coming out of the page, and then they are looping back and going through. So coming at you, going away from you, okay? Notice that if current is moving this way, right? If current is moving this way and the magnetic field is, for example, here into the page, okay, are those perpendicular? Well, you tell me, right? You betcha. Okay, same thing over here. If it's coming out of the page, right, are they perpendicular? You betcha. Okay, so let's use our hand rule to wrap our minds around this one. They've decided to go with current, so that will be our right hand rule. Okay, what does it tell us? So if I go this way, my finger's over here into the page, right? And then as I wrap back around, now my fingers are coming out of the page, right at you. Okay, so that makes sense. What if we try, what if we picture electron flow? Electron flow would be that way, and we use our our left hand rule. In L, L, L. Okay, left hand rule. Do we still get the same B field? Yep, into the page up here. What about down here? Out of the page at you. X's, dots. X's, dots. As long as you think about the charges correctly, you get the same magnetic field. Okay, What about this guy? Now we have our current going this way, so we'll use our right-hand rule, and really the same thing, right? We're just doing it on an angle now, but nothing's actually changed. If we take our left-hand rule and go the other way, same thing. We get out of the plane coming at us, into the plane going away from us. Tail feathers, arrowheads. Okay. Ooh, I like this one. Current is out of the board. Hey, we've seen something kind of like this, right? In fact, our current was actually out of the board when we did it on the real version, right? So if current is out of the board, current, which hand rule? Right hand rule, because current is what a positive charge would do, right? So current is out of the board. Now take your thumb, make it come out of the paper. Okay, and which way is the magnetic field? Just like they've drawn it there. From our point of view, it is counterclockwise, right? That's the opposite of the direction the clock would go. So, whoops, I'm not very good with my color coding. This should be blue if I wanted to be consistent. Okay, so like that, right? At any point on there, what does the B field look like at any one given point? Well, if I were to just say, what's the B field like here? It would look like that, right? What's the B field like here? It would look like that, okay? So overall, it is circular. Just like when we had a circular motion, like a ball on a string, and we swung it around, right? At any point on its path, its velocity was tangential to its circular path. So that if you cut the string, it just keeps flying off, right? If I take it like that, cut the string, it flies off circular. Sort of similar here, although of course it's a little different because we're talking about a magnetic field. A velocity is not a field, but same idea in terms of direction and visualizing it. The direction of the magnetic field will be tangential to that kind of circular path at any point along here. Okay, now here's an example where we've actually got to use our hand rule and figure it out on our own. We're not just confirming someone else's use of the hand rule. So this would definitely be one where I would usually say get up to the whiteboards, try it out, okay? So try it out. I would say pause the video, try it out. Think about the way you draw a vector in 3 dimensions, but then you can come back and sort of, if you're stuck or if you just want to check your work, come back and skip ahead or press play or whatever you want to do. Okay, so I'll set it up on the notes here, and then I'll go to a video of myself actually doing the hand rule so that you can see that, because it's not very helpful if you can't see me doing the hand rule, because that's all this question's really applying is the hand rules, right? So sketch the direction of a compass on the left side of a wire with an electron flow into the page. Okay, so first let's draw our wire, and then we can start to think about the magnetic field around it. So if we have a wire, if the electron flow is into the page, what does a wire look like? Well, it just kind of looks like a tube, right? Imagine a tunnel. Electron's kind of a tunnel, or sorry, a wire is a tunnel for electrons. If you're driving and you're coming up on a tunnel, what's it look like? Kind of just a tube ahead of you, right? Or I guess a circle, right? So if the electrons are going into the page, what are they doing? Well, electron flow into the page, right? Arrowhead away from us. So that is the direction of the electron flow. It's asking us what direction would a compass point if it was on the left side. So what is that kind of code talk for? Direction of compass? It's kind of just code talk for the direction of the magnetic field, B, right? So we're looking here and we're trying to figure out what will the magnetic field direction look like. So if you didn't pause at the very beginning, definitely pause now. Try to use your hand rule to figure this out. And then you can check your answer, but I'll go to the board to show you in case you're not sure how to do this. Okay, so here we have our wire into the plane of the page, right? The wire is looking like this. What are you seeing? You're seeing electrons head into the wire this way. And we're trying to figure out what does the magnetic field look like over here to the left. So first things first, electron flow, left hand rule or right hand rule? Well, if it's a negative charge, we use our left hand rule. If it's a positive charge, we use our right hand rule, right? So electrons, negative. So we're going to take out our left hand. Okay, thumb points in the direction that the charge moves. So we're going to take our thumb and we're going to make it do what the electrons are doing. So the electrons are going into the page, right? You'll get funny looks if you're doing this homework around your parents, but it is kind of fun, honestly. It kind of brings a certain physical level to physics that I like. Okay, so if our electrons are going into the plane of the board like this, or the paper if you're doing it at home, okay, what does the magnetic field look like up here? Well, it would be, according to our left hand rule, right, this way. That's not what it asked about. It asked on the left of it. So over here, what does it look like? It looks Now be careful, we're not going to use the word down because this gets weird quickly when we're talking about different scenarios. Always try to be careful and just talk about it in terms of the page. That is what most textbooks will do. That is what diploma type questions would say. They would say towards the bottom of the page or towards the right of the page. They wouldn't actually say right, left, up, down. Or then that way they can say into the page, out of the page, right? Because in theory, if you're looking down at a piece of paper, right, when you say down, right, if I'm looking, do I mean that? Do I mean down? Or do I mean down towards the bottom of the page? So just kind of be specific that way. So we would say, here's the magnetic field using our left hand rule to the left of the, I can't do it, it's hard to, oh, there we go, okay, that's better. To the left of the wire, it looks like the magnetic field would be towards bottom of page. Okay. So there we have that in the notes now. All right. Two parallel wires have current flowing in the same direction. Do they attract or repel? So again, I'll set it up here, then we'll go to our hand rules to think about it. You might want to pause this one and again, try it on your own. This one, there's a little extra step there. You got to think about how do a magnetic field interact? What does that mean for attraction or repulsion? Okay, so two parallel wires have current flowing in the same direction. So we have two parallel wires. Okay, two parallel wires, and they have current flowing in the same direction. So current, we'll go ahead and use actual current. We'll call it positive. Let's just say it doesn't matter as long as it's the same direction. So let's say it is coming, how about we do out of the page? So we'll do coming out of the page, little dots for arrowhead. So I'm just going to draw the end-on view from that. So seeing that as if your eye was here, okay, because that's going to be more helpful to us. So if I have two parallel, I just wanted to show you what it meant by two parallel conducting wires, okay? So if you're looking at that, it's going to look like this, okay? So pause it, think about the magnetic field, think about what that would mean for attraction or repulsion, and then you can skip ahead to my answer, my work, if you're not sure and get stuck or want to check or whatever. Okay, so here I've transferred from the notes to our whiteboard here, the two current carrying conductors that are parallel. So in this case, we have two currents coming out of the page, okay? So current, what kind of charge is that? Positive or negative? Positive. Is it actually positive charge flowing through the wire? No, but again, we took a gamble, we were wrong, that's okay, doesn't change anything, and we have to deal with moving positive charges anyway, so it's really no biggie, okay? Just remember that current is what a positive charge would do in a wire. Okay, so positive, so which hand rule? A right hand rule, right? Okay, now these are dots, what does that mean? It means they're coming at you. So we would take our thumb, our right thumb, point it out of the plane, right? So point it out of the plane of the page or the board in my case, and then we can think about the magnetic field direction all around. So as I rotate around, I see that, okay, obviously it's going to be circular so that it can be perpendicular to the motion. Again, why is it perpendicular? Well, if this is coming out like this is going like this, right? Perpendicular, okay, out like this, 90 degrees. Okay, so which direction though? Well, we have over here, okay, it looks like this. Up top, it looks like this. On the left, looks like this. Down here, looks like this. Okay, what about the other guy? Well, is there anything different here? This is actually the exact same situation, right? So again, we can double check if we're not sure, but think about it, right? We have over here, it's gonna be up. There, it's gonna be like that. Down here, it's gonna be like that. Down here, it's gonna be like that. Okay, so will these attract or repel? Now think about how we thought about attraction and repulsion with our simple bar magnets, right? We said, okay, if we have opposite poles together, attraction. If we have like poles together, repulsion, right? Okay, and it's kind of the same idea here. Since the magnetic field is kind of in the opposite direction where the wires are near each other, I almost think of it like these two are going, well, it's not even thinking of it. These two magnetic fields are going to interact in such a way where they almost kind of grab each other, right? Notice how one's coming down like that. They're kind of going to, as it comes around, whoops, as it comes around, they're kind of going to grab each other, right? And pull in, right? Picture two kind of gears turning next to each other, they'll grab and pull. What if the current, so what does that mean? Attraction or repulsion? Well, we're going to get attraction, right? Whenever we have the opposite field direction between the two carrying conductors, we have attraction, okay? I want to just draw this really quickly from above as well, okay? So from above, what do two current carrying conductors look like? Well, let's say now that we're just going to view this from the top down, okay? Now our current, would be, how about towards the top of the page through the conductor. So there's our I should really labeled that here too, I. Okay, current now is towards the top. So let's use our right hand rule. What do the field lines look like? Well, for this guy over here, right, if I point my thumb, my fingers are going into the plane. So X is over here. And then over here, what's happening? Aha, they're curling back around. They're coming out of the plane. So I got dots over here. Okay, what about over here? Same scenario, into the plane. So tail feathers. What about over here? Now they've curved back around. Notice my fingers are coming out of the plane of the board. So I got dots. I think I said we were looking at it from above, but you'll notice if you kind of try and match them up, we're actually looking at it from below, right? Because this one is going away from us. So we've looked at it like this, which makes sense when you think about it. These were going like this. So I've kind of flipped them up to go here. I flipped from here to here. So now you're looking at these from below when you look at this picture here. Okay. So again, now these are going away from us from below. Yep. These are coming towards us from below. Yep. That checks out. Okay. And again, when you look at these, match up this with this, right? We have opposites between the wires where the field will be strongest between them. Okay. And so that will be attraction. They will be pulled towards each other. So our answer for that question is attraction. Really quick, while we're here, let's think about it. What if this were an X? Okay, what if this were an X? Well, first of all, this would be wrong now. We'd have to change this, right? We'd have to change this to now say, well, if I use my right hand rule, okay, current is going into the page. So, of course, that just makes the magnetic field, instead of being counterclockwise from our perspective like it was before, it'll be clockwise from our perspective. So notice now we end up where between the wires where they're close to each other, we end up with a same direction magnetic field, right? And so if we kind of think about the attraction and repulsion, as we know from magnetic field interactions, okay, that will repel. Okay, those two wires will repel each other. Okay, if I were to draw it down here, now this one would look like this, which would mean the magnetic field would now look like this. Okay, so now I would have dots on this side, right, coming at you. And then on this side, they'd wrap back around, and now I would have X's. Okay, so no longer is that going to be attraction, right? No longer are they going to pull towards each other. Now you're going to have repulsion. They're going to push each other away. That actually looks like attraction. I should have drawn the arrows the other way. Either way, now we would have repulsion because we have field lines in the same direction between the two conductors. Okay, picture this kind of like two sort of things spinning, right? They're kind of going to no, right? Instead of catch each other like before. Now they're going to kind of push each other away. That's going to be the interaction of the magnetic fields. Okay, so the interaction of two magnetic fields, two or more magnetic fields, can actually provide a force, right? We will get there with a little more detail, but that shouldn't come as a surprise. We've seen these magnets moving stuff. How do you move something? It's still a force, right? Okay, but more on that later. For now, just accept that these two magnetic fields interacting will cause a force in this case because they're kind of bouncing off each other, right? This one that I've drawn would be repulsion. The one we originally did, the answer to the question, would be attraction because they kind of, since they're in opposite directions, they kind of, I think of it as they go around, they grab each other, right? As they're rotating, they kind of grab and pull onto each other. Okay, so there we go. Okay, In this case, they would attract. Just kind of a quick summary. Again, not really a fan of memorizing stuff, but it kind of helps to just have a quick boiling down of what it is. So when you have two parallel wires, okay, so in two parallel conducting wires, if you have two parallel wires, if the current or the electron flow is in the same direction, okay, so if the two currents in each conducting wire in a parallel conductors is in the same direction, so same charge direction as we just saw, they will attract, okay, because the magnetic field between them will be in opposite direction, right? It's the same charge direction, attract, because if you use your hand rule, the B field, the magnetic field, is opposite between the wires, okay? So if they have the same charge direction, you attract because the magnetic field is opposite between the wires. Now, what if we have the opposite charge direction, as we saw on the whiteboard, opposite charge direction? Well, then they're going to repel. Okay? Because why? Because the magnetic field will be in the same direction between the wires. Okay, so last thing for this topic, just a brief kind of preview of where we're going to go with this, is the connection of this first hand rule to the... Okay, so that wraps up our kind of topic 2 lesson. You can do a little bit more of 12.1, not a whole bunch. You can now do on page 592, so 6A8 on page 592, and that's actually it for this part.